Okay, let's get going. Welcome everyone to this Atacama Cosmology Telescope webinar tutorial. I'm Jo Dunkley, and on behalf of the collaboration, delighted to welcome you here and to hear about these new products and also way to access them that have been built by this set of members of our collaboration who are going to present today. You're going to hear from the list of people listed on this slide. And what we'll do is please, if you have questions, please type them in the Q&A, and then we'll have a chunk of time at the end to do questions and answers. And so with that, I'd like to acknowledge the NSF and its support of us, and then hand over to Will Coulton, who's going to tell us about the Compton YMAP. Thanks, Will.
Great, thanks for joining us. I'm going to be introducing the data sets used and also the methods we've used to produce the Compton YMAP from our observations. So as I'm sure you would guess from the name, the Atacama Cosmology Telescope, or ACT, is located on Cerro Toco in the Atacama Desert in Chile. This site is about 5,000 meters above sea level, and is a very dry site, which makes it a great place to do CMB observations. As a result, in addition to ACT being located on this site, many other experiments that you might be familiar with, such as Polar Bear, CLASS, the upcoming Simons Array and Fred Young submillimeter telescopes are located in the vicinity here. And just on the neighboring mountain is ALMA, that some of you will also be familiar with. So what is ACT? Well, actually, ACT finished their observations almost a year and a half ago now, at the end of 2022. And the instrument, as pictured here, has actually been removed from the mountain. And we're now working on analyzing all the data that is collected over its 15 years of operations. So ACT was a 6-meter high-resolution CMB experiment that observed the sky in 5 frequencies ranging from 30 gigahertz all the way up to 220 gigahertz. The data we're going to be presenting today is focused on the 3 high-frequency bands, one centered around 90 gigahertz, a second around 150 gigahertz, and the final one around 220 gigahertz. In addition to being high resolution, ACT is a very sensitive instrument and now has reached medium map depths of around 10 microK arc minute. And in addition, it covers a very large area of the sky. The full footprint covers almost half of the sky. But what I'll talk about today is roughly observations on about a third of the sky, which is obtained from observations pointing away from the galactic plane. So we describe ACT as a cosmic microwave background, or CMB experiment, but really when we observe the millimeter sky, there are a plethora of different signals that we observe, and this can be seen very clearly in this image, which shows observations of the full sky as obtained by the Planck satellite, ranging from 30 gigahertz here to 857 gigahertz. You can clearly see as the observation frequency changes, the signals, particularly from the galaxy, change. So at low frequencies, our observations are dominated by synchrotron and free emission. And at very high frequencies, we switch over to being dominated by emission from galactic dust. In the units of these maps, the CMB, which is visible at the high latitude regions, has a constant amplitude. In addition to the changes of the different signals with frequency, I think it's very clear from these images that the statistical and spatial properties of different signals is very different. In particular, as we would expect, signals from our galaxy are typically concentrated in the galactic plane. So these are very anisotropic, and they're also highly non-Gaussian. In contrast, the CMB anisotropies are statistically isotropic and highly Gaussian. In addition to the galactic signals that I just discussed in the cosmic microwave background, there's also a range of really interesting extragalactic signals that are present in our data sets. This includes emission from high redshift dusty star-forming galaxies and radio galaxies, and CMB secondary anisotropies, which are anisotropies imprinted upon the statistics of the cosmic microwave background as they propagate through the universe from the surface of last scattering to the observer here today. One of the most well-known of these is gravitational lensing, which describes how the trajectories of the CMB photons are deflected by intervening matter. And there will be a webinar tomorrow talking about recent ACT measurements of CMB gravitational lensing. In this talk, we're going to focus instead on signals known as the Sonaer-Savdovich effect, which arise from the interaction of CMB photons with the gas in galaxy clusters. What I'm showing here is a cutout of the Webb sky simulations, which show simulated observations of several of these extragalactic sky components. So we have the thermal and kinetic Sonaer-Savdovich effects on the top, gravitational lensing, and dusty star-forming galaxies, bottom right. What is clear is that the statistical properties of these maps are also different from both the galactic and CMB anisotropies. In particular, on large scales, these look largely isotropic, but on small scales, you can see that many of these maps are highly non-Gaussian. This is perhaps most evident for the TSE effect, where you can see the imprint of individual galaxy clusters, such as one here in this zoom in. In addition to galactic and extragalactic components in our observations also include noise. This comes both from our instrument and from emission from the atmosphere. What I'm showing here is an observation depth map now from a few years ago from ACT, which shows in red areas in which the experiment observed for longer. What you can see here is that there is clearly a high degree of anisotropy in how long we've observed in different areas of the sky, though this has become more uniform as the experiment has progressed. This means that the instrumental noise itself will also be highly anisotropic, varying from much lower levels to much higher levels, depending on the amount of observations we've had there. Finally, the noise, in addition to varying in location in the map, actually varies as a function of scale. What I'm showing here is a rough measure of the standard deviation of the noise as a function of angular scale or multipole moment. Multipole moment is inversely proportional to angular size, so small angular scales correspond to large values of the multipole moment. Sort of arc-minute scales roughly over here and degree scales over here. What you can see is that at very small scales, the ACT noise is approximately white and in its lowest regime. This is when it's dominated by noise from the instrument. However, as we try to measure very large scales, the noise blows up, and this is due to large contributions to our noise from the atmosphere. Fortunately, the large scales of the sky have been observed by other experiments. In particular, in this work, we consider the Planck data, which I showed earlier. And Planck has made really pristine measurements of the large-scale CMB anisotropies, as you can see here, where the noise is significantly lower than the ACT noise would be. And so we will exploit this complementarity in this work to combine data from ACT plus Planck to get the best of both worlds and to be able to reconstruct the Compton Y map across a really large range of angular scales. So bringing all of these pieces together comes the idea of component separation, which exploits the fact that many of these signals have different frequency dependencies, as we saw earlier, or statistical and spatial properties, such as the galactic signals being concentrated in the galactic plane. And the idea is to exploit these different attributes of the different signals to isolate one component of interest from the remaining signals on the sky. This is often very useful, as it will allow you to analyze that signal without contamination, either noise or bias, from other sky signals. And additionally, you can potentially isolate small signals that could be dominated by otherwise bright signals. So the method we've used in this work is the internal linear combination method, or the ILC method. And this method is very simple to explain how it works. The idea is that we model our observations D at frequency nu in terms of the component of interest, S, and a frequency response function, which tells you how that signal of interest contributes to your observations at frequency nu. Then we describe every other sky signal, be it actual noise or other sky signals, as a noise term here, N nu. The IRC method seeks a linear combination of our observations that has the minimum variance and is given very simply by this equation shown here, which is a linear sum over our observations at different frequencies, where C here is the covariance matrix describing how correlated observations at two different frequencies are. So in our work, we are presenting a map of the Compton Y anisotropies, which isolates the thermal Sunyaev-Zavdovich effect. The thermal Sunyaev-Zavdovich effect, or TSC effect, is caused by the inverse Compton scattering of CMB photons of hot electrons. So a CMB photon propagating through the universe will interact with hot electrons, and it will gain energy and upscatter them, their frequency distribution to higher frequencies, as shown here. When we work in CMB units, which compares the measured size of the signal to what we would expect for the CMB black body, what you see in this case is that at frequencies below this null frequency of 217 gigahertz, you would see a decrement. You see fewer photons compared to what you would expect for the CMB black body. Whereas above this null frequency, you see an excess of CMB photons. This can be shown here in this bottom video, which shows measurements of a cluster by Planck, where at low frequencies, you see this blue negative signal, which goes to 0, and then a red excess above 217 gigahertz. More specifically, our anisotropies, as we observe them in our map, will depend on this frequency function and a parameter that we call the Compton Y parameter. The Compton Y parameter tells us about the integrated line of sight pressure along that direction in the sky, N. This is really powerful both as a cosmological probe, as I'll show, it's a very useful way of identifying galaxy clusters, but also through its dependence on the pressure, a really interesting probe of the astrophysics of these objects. So what I'm showing here is the result of applying our IRC method to data from ACT plus Planck, and has isolated the Compton Y map over scales from the larger scales down to arc-minute scales. As I said, the Compton Y effect is sourced by regions with high pressure, and this is dominated by gas in the intercluster medium, which is incredibly hot and dense. So each one of the white yellow dots that you see in this map here and here is actually a galaxy cluster that you can see by eye. So for example, this would be the Virgo galaxy cluster. As you can see, this map covers a very large part of the sky, roughly about a third of the sky. To dig into the details a little more, I'd like to highlight what the benefits of having high-resolution ACT data could be. And so to do that, I've shown a zoom in on the previous map, but as made from only using Planck data. And now on the next slide, we'll compare this to our ACT plus Planck map shown here. As I transition between the two, you'll see many structures, such as this, for example, are coherent between the two and pop out more in the ACT map, which has higher resolution and lower noise. There are some structures, however, noticeably this diffuse region here, which disappear in the ACT plus Planck map. Looking at the high-frequency Planck data, we actually see that there is a very large clump of dust in this region, as shown here, that traces out the diffuse structure that disappears. So this really highlights the benefit of adding higher resolution, low frequency data from ACT to the high resolution Planck data. More quantitatively, we can compare this by looking at the power spectrum, which measures the variance as a function of scale. Again, to remind you that L here is inversely proportional to angular size, so small angular scales correspond to large values of L over here. We compare our measurements. The measurements of the power spectrum are shown in green here from the Planck-only data, with our ACT plus Planck map shown in blue here. And really what you can see is that on very small scales, there is a really dramatic improvement that comes from adding the really high-resolution data we have from ACT. The second thing to notice is that our measurements lie significantly above the theoretical prediction for the power spectrum over almost all scales, which says that our map is effectively noise dominated on almost all scales. This highlights how non-Gaussian the Compton Y map is that we can, by eye, locate individual objects, but we're not able, but that the power spectrum is noise dominated. And with that, I'm going to hand you over to Adri, who's going to talk about simulations of our Compton Y maps.
All right. Thank you, Will. Yes, so I will talk about simulations. So simulations are important in this type of analysis. And the main reason for that is that the ILC method produces a best fit map of this Compton Y parameter, but it doesn't directly give you an estimate of the uncertainty on that estimate. So this is where simulations come in. We can use simulations of the data to then, in subsequent analysis, quantify this uncertainty. And to help you with this, we've created various types of simulations. I've illustrated them here on the right. So I took at the very top right, you see a part of the actual data. This is just a small cutout. And then below that, I flip between versions of simulated data that we've made. These contain both simulated signal and simulated noise. And at the bottom, you then see simulations of what we think the noise in these maps is. We make these simulations publicly available, and I'll tell you where you can find them. All right. So these simulations, roughly speaking, aim to model two effects. And the first effect is the noise properties of the map. So Will already touched upon this a little bit. The idea is that because these maps are a combination of the Planck data and the ACT data, and for the ACT data, we use both the most recent ACT data, which covers a fairly large part of the sky, which is depicted in this top image here as this red, the big red patch. But we also include some of the older ACT data, which observed smaller patches of the sky, and that's depicted in the figure here as the small colored patches. So you can imagine that once you've combined all of these data sets, the resulting noise properties are a little bit complicated. For example, illustrated here at the bottom, you see the inverse noise variance per pixel of the resulting map. So here the darker pixels are the most sensitive pixels. And you can see that this traces these different patches quite well. But it's not just the per pixel noise variance that changes over the sky. There's also a bit of a spatial dependence to the noise power spectrum. And there's also a spatial dependence to the amount and the directionality of stripy noise features in the map. The second thing that the simulations aim to capture is signal residual. So from the point of view of this Y-map analysis, the cosmic microwave background and the cosmic infrared background and our own galaxy, they all serve as contaminants. And of course, their amplitudes are reduced quite substantially through the whole ILC process that Will just introduced. But these contaminants are not completely removed. So their residual acts as a sort of second set of noise or second type of noise. And it turns out that this second type of noise is a quite significant contribution to the total noise in the maps. So we released two types of simulations. The first one are these end-to-end simulations where we aim to mimic all aspects of the data. And the second type of simulations are noise simulations where we just aim to simulate the noise in the maps. So starting with these first types of simulations, they consist of three parts. First, we take our best estimates of the Planck and ACT noise. We then add on top of that galactic signal using the PySM library. And then finally, and most importantly, perhaps we add extragalactic signal using two simulations, the Webb Sky and the Segal simulation. So these contain the extragalactic contributions to the microwave sky. So, for example, the cosmic infrared background, but also the TSZ signal that we're after itself. And you can see here at the top right again a little image of the resulting simulations. So it's important to note that we only have a few of these simulations. That's because we only have a few of these extragalactic signal simulations. So we release 4 simulations plus some extra variants with slightly different noise properties. The second type of simulations are the noise simulations. So to create these, we take this pipeline for end-to-end simulations, where we've replaced these non-Gaussian signal simulations that I just talked about with Gaussian signal simulations. These are simpler to model and allow us to draw a few more simulations in order to build up the statistics that we need to estimate a noise model from which we can then draw additional simulations. It's sort of a generative model. And from this, we generate 300 simulations, but we also release the tools to generate additional simulations if your analysis requires that. And these simulations are very quick to generate. So then finally, where to find the simulations? So we've hosted them on the NERSC cluster, and they're publicly available to everyone, and you can find them at this URL. So if you would click on this URL, you see these 3 folders with the noise simulations I just talked about, these non-Gaussian end-to-end simulations, and then there's also a copy of the data itself. If I quickly demonstrate that, so here's this folder, and I would just want to highlight, if you go to the noise simulations folder, you also find a second sort of set of instructions here with more information about the actual simulations that we provide, some extra background on the methodology, some details of the resulting maps, some instructions of how to load the maps into memory, some instructions of how to reproject the maps to different geometries if you would like to do that, and then finally instructions of how to draw additional simulations. All right, that was all from me, and then we will move on to Maya, who will talk about some of the notebooks.
Yes, thank you so much. So I'm going to share my screen as well. Great. So I am going to talk a little bit about some of the data products that we have with this release and where to find them, as well as where to find notebooks that we release to help users kind of learn how to do analyses with these Y maps, as well as with some of the other data products if you're interested. So if you were to look up Lambda and the Atacama Cosmology Telescope, you would find this web page here, which has a list of all the kind of data products ACT has released over the years. And if you scroll down, you'll see this section here that says data notebooks and Jupyter Notebooks tutorials associated with the ACT DR4 and DR5. So this is our older set of Jupyter notebooks that we released a while ago that you can find on GitHub. And these walk through some of the kind of basic introduction of how to use ACT data sort of more broadly and how to do common analyses. So those are always available for anyone interested. In addition to that, with our most recent data release, we've compiled some more of these notebooks that are available for everyone to use. So if you go up here, this is the Compton Y map we've been talking about now. If you were to click on the actual Compton Y map here, you get to this page, and this gives you links to download the actual Y maps we've been talking about, as well as the mask and the effective beam response associated with these. You can also click into the detailed product description, and here you get a little bit more of an explanation of the actual maps. There's a link to the data products that Audrey showed before here that you can click on to get those simulations if you're interested in them. And then there's also a link down here to the GitHub page, which has notebooks demonstrating how to use these Compton Y maps. So if I click over here, you get to the GitHub page that has all of these notebooks, and you'll see for the DR6, we have notebooks both for lensing and also for these Y map notebooks. If you were to click on any of these notebooks to open them, you would get links to open them in Google Colab, which means that you can run them online very easily. There's no need to download any packages or data to your kind of local machine. Instead, they can run directly kind of on the web with the Google Colab notebooks, which is really great. They're super easy to use for that reason. I do want to kind of highlight, though, that if you're interested in using these data products and these analyses in a kind of maybe more robust way or using more data, you probably want to kind of transfer this code to a cluster or a NERSC or something like that in order to run this code, because most of our analyses are not done in these kinds of notebook formats. They're done at scale on these clusters. But this is a great way to get an introduction to these notebooks. And again, if you're kind of interested in slightly more intro level notebooks, there's also the DR4 and DR5 ones that are available and available from Lambda. So now we want to take a moment to look at these notebooks in a little bit more detail. And I'm going to hand over to Martine, who's going to talk to you a little bit about one of the notebooks we have looking at the Compton Y maps.
Great. Thank you, Maya. And I will share my screen with that notebook now. All right, so as Maya mentioned, here we have a couple of YMAP notebooks, and I'll go over this YMAP stacking notebook. And if you click on it, it'll take a couple moments to load up, but then we'll see a little button come up that brings us to this option of open in Colab. So if I clicked on that, I already have it open, but we'll get this Colab notebook like this. So you're welcome to follow along if you'd like, but I will just be scrolling through with the pre-computed outputs for now, since it does take some time to run. So this notebook is made to show how to visualize objects in the YMAP, in particular galaxy clusters, and also give a demonstration of stacking a few galaxy clusters and looking at their profiles. So we start off with a little bit of information, including the links that Maya mentioned that are repeated here just for ease of access. And in the first section here, we're going to pull in the YMAP here, as well as the mask in this next line. So this accesses the full YMAP and mask, but if you'd like to run the notebook more quickly using less memory, you can run these lines instead, which are going to point to some downgraded maps that won't take as much memory. And there's a couple of other options to load the maps in these ways afterwards. Once we have those, we're going to install a couple of packages. As Maya mentioned, this is doable totally within the Colab framework. So this pixel package is going to allow us to read in and manipulate the maps. And this pillow package is just for some image manipulation for this particular notebook later on. Once we've imported our relevant packages, we're going to read these in as nmap objects from the pixel package again, and we can plot them here. And now we see that we can see the two regions of the YMAP. And in this map geometry, which is in the CAR format, we can see that the sort of lower declination regions appear, distorted, stretched out, because of the sky geometry. But this is the native format of the ACT YMAPs, and this notebook shows that you can do lots of things in this native format without needing to convert to HealPix maps. But if you are interested in doing analysis with HealPix instead, there are examples of how to reproject the maps into HealPix, and the notebook to do so is linked there from those earlier notebooks. We see the range of the Y scale down here in the color bar as well. So next, we're going to get a publicly available cluster list. Here I've chosen the Dark Energy Survey Y1 set of red mapper clusters to load in, but you can replace this with whatever set of objects you'd like to check out. And I'm going to limit those to a minimum richness of 20, so fairly massive clusters, and clusters below redshift of 0.5, just to make sure we're looking at low redshift, large, massive objects that are going to be easily visible in our map. So after doing that reduction, we have about 3,900 clusters left. Here we define a function to show the location of those clusters on the map. and we can view those here. So those are all of these little white points in this southern region and the northern region up here. This is again from the year 1 DES footprint, so it's not, at that point, it wasn't totally filled in yet. And one thing to note is that the clusters in the lowest declinations are actually running over the edge of the ACT map because the DES footprint extends slightly further in DEC. And so for an analysis, what we probably want to do is cut down those clusters to be well within the edge of the ACT footprint so that we're not using any sort of partially masked or fully masked pixels in our analysis. And the next section shows how to do exactly that to see if our objects are near edge of the Y mask. Briefly, what we do here is define a threshold of 2 degrees from the edge, set that up here, loop through our clusters here, check basically if a small cutout in the mask surrounding each cluster has a mean of less than 1. And if it does, that means some of those pixels were masked. And so we're going to remove those clusters from our sample. So at the end, we have 3,400 clusters remaining. And we can see in this image here that we've cut out the clusters close to the map edge and also away from the masked regions of the ACT Y map that are shown in these little holes. Now that we have that sample, let's take some cutouts around some clusters and look at how they appear in the Y map. To do this, we're going to define a submap, which we're going to look at in a patch size of 1 degree per side. And here I'm going to show just the first 10 clusters in this cluster catalog. And I'm printing the area of that patch in steradians, the size in pixels, the richness of the cluster, its redshift, and its RA and DEC here. And the purpose of this is to show, first of all, these are very high richness clusters we're going to see. So very high signal to noise in the map. So as Will mentioned, even though the map is noise dominated in terms of its power spectrum at almost all scales, we can see individual objects like these really massive clusters very well. And so we can do lots of analyses with them, especially when we have an external catalog. The other thing to note is that each of these patches is going to actually have a bit of a different area. And that's because, again, of that geometry, the car geometry of the map. So these have the same pixel size, but each of them is a different area because we defined a constant radius in RA and DEC. So because of that, you might notice that some of these appear a bit squashed, the lower DEC objects. And in the next section, we're going to deal with that for an example of a stacking analysis. Okay, so for some example stacking, let's take those 10 clusters and now do the proper reprojection to make sure that we are treating them each equally and fairly before stacking them. To do that, Pixel has this handy reproject.thumbnails function that we're going to use to reproject the map around the location of each cluster with our desired radius, which is going to be a patch size of 1 degree again. And now we can see those clusters once more without the distortion in the lower DEC regions. We can also see, as I'm printing the area in steradians, that that is now constant, and it's all equal pixel sizes as well. So we can very simply average over all of these stamps and get our stack. So in this section, we're going to do that. This is just a simple average. Of course, if you wanted to do this in a more complex way, you could do something like signal to noise weighting. And we'll plot that stack down here. So I've shown that on the right. And I've also shown the example of what that would look like if we didn't do the reprojection, just to show how it would look a bit squashed in the horizontal direction. So we can see our average of those 10 clusters here, and it's peaking at nearly 1 times 10 to the negative 4 in Y. And again, it's 1 by 1 degrees. Okay, in the next section, we're going to look at the profile of that stack. And there's a function here to get that in terms of annuli as you go outwards. Something to change is, for example, the binning in here if you want to work with the notebook yourself. And so we're going to loop through calculating the average y in the different annuli and get this profile in blue. And the errors are just given by the standard deviation of all the pixels in each annulus. So it's a very simple example. And here I'm showing also the 1.6 arc-minute Gaussian beam, which is the resolution of the ACT map, to demonstrate how this cluster profile is extending well beyond the beam. So we're actually seeing information about the cluster, not just the beam. And in the last section, because these clusters are all actually at different redshifts, of course, in a scientific analysis, you might want to take cutouts of constant physical size. And so we can import our desired cosmology from, for example, AstroPy, and calculate what the angular size of the relevant physical size would be at the given redshifts in this line here. And when we go through that and take all of our patches, including the reprojection, we're going to see that our patches now have different sizes in terms of number of pixels. So the next section just gives an example of how you can rescale and interpolate your images to make a stack that has the same shape. So here's our stack in constant physical size. So we can see this is 10 by 10 megaparsecs in this example. In the last section, again, we look at a profile, in this case, plotting it with a log scale in Y. And finally, we look at how much the noise in that profile improves in the full stacked image versus in all of the individual cluster images. Because we can see by eye that the signal to noise has improved visually. So to quantify this, we just look at, again, the standard deviation in those annuli in each individual cluster image profile versus the full stack. And we can see, comparing those colorful curves to the blue ones here, that we've had a reduction in noise, and so increase in signal to noise. With stacking, you generally expect that to be square root of the number of stacked images if all of your images have the same properties, the same signal. So we'd expect it to be about 0.3 times the noise in any individual image. In this case, we get 0.4 times, and that's just because we have, slightly varying clusters in our sample of 10, and it's a fairly small sample size. But overall, this notebook shows an example of the great kind of cluster images and high resolution we have in this map, an example of a stacking analysis that you can work with. And just to mention, if you do want to work with this, you can make changes directly to the Colab notebook, but if you try to save, it'll say cannot save changes. And if you do that, you'll just want to go to save a copy in Drive to do it in your own drive, or you can add it to your own private GitHub repository and work with it however you'd like. If you find any issues, please feel free to open up an issue on GitHub or contact us. And next, we're going to move on to Ola Kuziak, who's going to talk about another example of a notebook that shows how to work with the deprojected maps.
And actually, just quickly, Martine, because we have a question that was relevant, a detail about your one. There was a question about whether you get the richness from the map or the catalog when you do the stacking.
Okay, great question. Yeah, that richness is just directly imported from the DES catalog. So they have their own measure of richness based on cluster members. So yeah, that's an external factor in here.
Thanks.
Thank you.
Great, sounds good. So now I'm gonna share my screen and talk about mitigating the CIB contamination in the Compton YMAP. All right. So as Will was saying, the ILC procedure allows us to make maps of the signal of interest. However, this method treats all contaminants as noise. So if these contaminants leak into your final Compton YMAP, which happens quite often, they can bias your analysis. For instance, when you're cross-correlating your Compton YMAP with some large-scale structure. Fortunately, we can remove those contaminants, assuming we know their spectral or spatial dependence, by adding constraints to the ILC using the method known as constraint ILC. There is, of course, no free lunch. We cannot just keep adding more and more constraints and removing no contaminants, because as we do that, we are increasing the noise of the final map, which can be seen on this plot here. So in the base case, based on that ILC, this map has the lowest noise. And as we add one more constraint, when we, for instance, deproject, this is the name of removing the CAB, adding one more constraint, the orange line has slightly higher noise. And when we add one more constraint of deprojecting this d beta, this map has the highest constraint. So adding more constraints, deprojecting more foregrounds increases the noise of your final map. And I'm gonna now walk through the notebook that illustrates the potential CAB contamination in the Compton Y map. But first, let me talk about CAB. So CAB is this cumulative thermal emission from star-forming galaxies that peaks around redshift 2. And as I said, it can be removed during the ILC procedure, assuming we know its frequency dependence or its SED, which typically is modeled as a modified black body, which we parameterize by the spectral index beta and the temperature of the CAB, T CAB. And in the DR6, we provide various values of the beta and T CAB for the CAB SED, which are listed here. And now I'm going to walk through the tutorial. So here we investigate the potential CAB contamination in the Compton Y map when correlated with large-scale structure, where in this case we chose the publicly available dark energy survey or DS year 3 data, the cleansing map from the highest redshift bin 4. And for the Compton Y maps, we're using the standard Compton Y map from the Colton et al. Paper, as well as 2 maps that deproject CAB with 2 different values of both beta and TCAB. We also use the standard masks from both DR6 and from DES, as well as we know that all Compton Y maps have 1.6 arc-minute effective beam applied to these maps. All right, so here, first we import all the necessary packages, which are similar to the notebook that Martin presented, with the only difference that now we also want to import this Namaster software that allows us to compute cross correlations between 2 different maps. So once we import all those packages, we would also like to download the necessary maps to run this notebook with the wget command. And for this notebook, I downgraded all of these maps by a factor of 10 for computational efficiency, so it's easier to run all these computations in the notebook. But in real analysis, you of course want to get the full versions of the maps. So once you get all of those maps, you can put them into your Google Drive and access them directly from there and inspect the maps. So here's the Compton Y map from the ACDR6 data release that we already seen, shown using the pixel package. And similarly, here's the DES year 3 kappa map from the highest redshift bin. This map has been reprojected from the native Hill Peaks format to the CAR format that we use for DR6, and then also downgraded 10 times. So you can see the characteristic shape of the DS footprint here. So then the next thing we would like to do is to use Namaster to compute the cross correlation between the 2 fields. So first we create these Namaster field objects, put the maps, the Y map and the DES map here with their respective mask. We know that we would like to deconvolve the beam for the Y map. And once we do that, we would like to define the binning that we would like to use for our cross correlation in the Fourier space. So we define the initial and the starting and ending L's for our bins. And once we have that, we feed these namaster fields as well as the binning scheme into this namaster compute full master function. And that's all. That computes the cross correlation between the two maps. If you don't want to wait, because it might take a couple minutes, you can just load the pre-computed values for the cross correlation between the Y map and the kappa map from DES, which are here. Okay. So once we have that, we can of course take a look at the plot the cross correlation. So here is how the cross correlation looks like. It looks fine. It's positive, increasing at small scales. Everything looks great. So now let's try to investigate how things look like when we deproject CIB. So in this section of the notebook, I'm using the two other maps that deproject CIB. Here's a quick summary of how CIB is modeled in the deprojection that I showed on the slides as a modified blackbody. So I'm not going to go through that again. And here we take these two maps that deproject CIB. The first map has a value of beta of the spectral index of 1.4 and the temperature of 10.7 Kelvin. And the second map has the beta value of 1.2 and temperature of 24 Kelvin. So we load those two downgraded maps, put them into namaster field objects, and again, compute the cross correlations, where you can simply load the pre-computed values. And here's how the different cross correlations look like. It's interesting to see that for different values of the CIB parameters, when CIB is deprojected, the final cross correlation might differ, which might point us towards the fact that the modified blackbody might not be the best model here and doesn't capture the variations in the CIB SED that might arise with scale and redshift. But just to be sure and quantify this difference, let's also add error bars to these cross correlations, which we're also going to do with the namaster package. We're going to compute namaster Gaussian covariance and get the error bars from that. So here is a little function to interpolate the power spectra at every L, which we need to put into this namaster Gaussian covariance function. And this directly outputs the covariance from which we can get the error bars from the diagonals. Okay, so we do it for both cross correlations for both Compton Y maps. And here's the actual final cross correlation with the error bars. So as you can see, the cross correlation might differ significantly depending whether we deproject or not deproject CIB, and with what value of the CIB parameters, with what values of beta and T. And the question, of course, arises, should I deproject CIB? Should I not? With what values? And unfortunately, we cannot provide a firm answer because it's going to depend on the sample that you're cross-correlating your Compton Y map with, the properties of that sample, what redshift it's in, and so on. So unfortunately, there is no one general answer of what Compton Y map you should use. However, in a case like that, when the final cross correlation is not stable to the choice of the beta and T parameters, what we would recommend to do is to use the so-called first moment deprojected maps, which are also available in the DR6 data release. So yeah, when modified deprojecting CIB as a modified blackbody is not enough, we recommend to also use the maps that deproject the derivative of the SED with respect to the to beta or T, basically also deproject the first moment of the Taylor expansion of these parameters. So in such a map, we will not only deproject the CIB as a modified blackbody, but also the derivative of that SED with respect to beta. And you can see an illustration that it works quite well on this plot here, where we show a cross correlation between the Compton Y map from ACDR6 and the and unwise galaxies. So in the case of the baseline ILC in gray, we just get some cross correlation. And then when we check how this varies when we deproject CIB with different values of beta, which is shown as these dotted lines, you can see that there's a lot of scatter in the final map, which again points us to the fact that in this case, the modified black body might not be the best model here. However, when we also, on top of deprojecting CIB, also deproject the derivative of the beta parameter, and this is shown as these solid lines, this is quite stable to the choice of the beta parameter, which probably means that this is the most robust way to mitigate the CIB contamination. So the point of this notebook is to just make everyone aware that CIB should be treated with caution. And given how small our error bars get with ACT-DR6, we should definitely think carefully about mitigating CIB. CIB is also not just the only foreground that we should take into account. Other examples include non-masked radio point sources or ISW effect that also should be treated carefully. And just to summarize everything, again, all the data can be accessed through Lambda. It's available publicly on Lambda. And the notebooks for both YMAPs as well as the lensing notebooks are on ACT GitHub. So with that, I will end, and we are happy to take any questions.
Thank you very much, Ola, and all the speakers. If you have questions, please just pop them into the Q&A boxes, and we've got a couple coming up. I guess the first one for Will is a question about the mask. The question is does it select the survey region and mask out bright point sources, or does it mask out anything else? Can you say a bit more about what's in the mask?
Yeah, so that mask is mostly just the survey area mask, and it masks out a couple of really bright extended sources, which were the sort of 5 or 6 holes you saw in the rest of it. So for point sources, there are 2 other masks provided in the directory link there, because we have different treatments for different types of point sources. So really bright point sources are in-painted in our pipeline, and there is a mask that shows which sources have been in-painted. Sources that we're able to detect but aren't, sort of 50 sigma sources, these are subtracted in our map-making procedure, and there's a second mask which shows which masks out those objects. And so depending on your analysis and what you're worried about, you can use some different subsets of those maps. Masks, sorry.
Thanks. And for I guess Martine, you and Ola both talked about the overlap with Dark Energy Survey. Could you say a bit more about what other surveys, what we have overlap with the ACT data with other surveys?
Sure. So off the top of my head, I'm familiar with, for example, DESI. So we'll have partial overlap with the fairly new DESI data in the northern part of our footprint. I believe the same goes for BOSS CMAS data, where we have partial overlap in the more northern region. I don't know if anyone else wants to add a couple more surveys.
Probably also HSC, although it's by itself a small footprint, I believe we do overlap with HSC.
Super, thanks. And just to clarify for Adri, you spoke about the NERSC access to get the simulation. So all of the data products, the data products are all on NERSC, and if you don't need an account, but if you have an account, can you just grab those files over? Does one need to copy them into your own space or anything?
Exactly. So there's 2 ways. This public URL allows you to download the files to whatever, and then if you have an account on NERSC, you can also just navigate to those folders there and work on NERSC or, yeah.
Wonderful. And again, Maya, you just confirmed that as well. You can use HillPix. You can use our examples of how to work either in this pixel format or in HillPix.
Yeah, a lot of our actual analysis examples will use Pixel because that's what we use for a lot of the analyses within ACT and what we would recommend with our maps. But there are examples of kind of converting maps to and from HealPix in those DR4 and DR5 notebooks. So if you have another map in HealPix you want to try using in Pixel, you're welcome to do that too. I also wanted to mention, if you're interested in the other notebooks that I showed in the DR6 GitHub there's a webinar tomorrow at 11 a.m. Eastern time talking about the other lensing notebooks that are in that repository. I'm sure Joe is going to mention it anyways.
Super. Do we have any more questions from people joining online? I'm not seeing that now, so I think we will draw it to a close. Yeah, thank you everyone for joining, and we will post this recording also on our website and link it from Lambda as well. So if you are getting to grips with the data, go and watch it again and see what people say. And indeed, there is a lensing webinar tomorrow at 11 Eastern on the lensing products. And thank you to all the speakers. All right, goodbye.